Hi guys, welcome back to Data Every Day. Today we're looking at a data set of gas prices in Brazil, uh, basically a bunch of different sales data, and we're going to try to predict what the type of product of a given sale. So it's a bit of an unconventional task. I don't know how particularly useful it would be to be able to predict the kind of product, but it's interesting to pursue these sort of unconventional paths. And I also like to pick tasks that have a high probability of um, having good performance. I don't want to pick something that, for example, I don't know. I don't want to pick something that's going to give us like an accuracy of 20 to 40%, even though it's probably more useful than this. So we're just going to go with this. Given weekly reports of gas sales, let's try to classify the type of a given product. And we'll use a TensorFlow artificial neural network to make our predictions. So I'm going to import some of these libraries. We got NumPy and Pandas. As always, we have matplotlib, pyplot, and Seaborn for visualization. Then for pre-processing, we have label encoder and standard scaler from sklearn, along with the train test split function and the class weight from the utils, all for pre-processing. And then we will have TensorFlow to train our model. Alright, so let's load in our data using pandas.readcsv. And we can get the file path right over here. Paste it in. We'll take a look. And right away you can see we have everything in one column. And the reason for that is we can see it is actually tab delimited. So normally the delimiter is a comma. So we have to make sure we specify the delimiter here is a tab. Now it loads in properly, and you can also see that we're missing some columns. We can't view them all, so I'm going to go into the console and type pandas.setOption max columns to none. Alright, now we should be able to see all the columns on one data frame. There we go. And we have, this is pretty good. I'm just going to get a little information here. Alright, looks like most of our data is numerical. And again, this is the column we're trying to predict, product column. A lot of these are all in Portuguese. We have translations here in case we need to know what each one is. But there's a few things I noticed right away, which is that we have the month and year columns here, which are sort of duplicates of, well, not duplicates exactly, but this is sort of giving us a week idea, because all of these are shown, like the month and year of these are already captured over here. So the only useful information is the days. This like 09 to 15, 23 to 29. You can see it's a period of 6 or 7 days between the initial date and the final date. So we have to think, do we want to keep these columns? Or do we want to create a new week feature from them, or do we want to just drop them completely? So it's a bit weird to consider a week feature because what would a week feature mean? It would be, okay, so you could think of it as time of year, but the month sort of gives us that already. Time of year is already captured in the month. You could think of it as time of month, whether it's the first, second, third, or fourth week in the month. But how useful is that? It may be useful. There's certainly a way we could do this. All we'd have to do is, well, we could probably take a period of 30 days and then divide that into 4. And then if the initial day is within a certain quantile of the 30 days, we could assign it to a unique time of month feature. But I don't know if we want to do that. It just seems like unnecessary information. Although, given if we really want to get as much performance out of this, we may consider keeping those columns. But for our purpose, we're going to drop these two, the initial date and final date. We're also going to drop this, which is just a duplicate index column. So let's do this pre-processing, and I'm going to make this unneeded columns, is going to be so unnamed 0, and then these two. And I'll grab it up here. Alright, and then we're just going to do data.drop unneeded columns. Axis 1. Okay, now let's take another look. Alright, now we are left with the rest of our features. Now, we want to see, okay, how many null values do we have in this? So I'm going to check. First I'm going to check the total number of null values, and it's actually 0. So, from what we can tell, there are no null values in here. If I want to check the number in each column, you can see that there are no null values across the entire data frame. Alright, so let's do some visualization, just a little. I'm going to visualize the class distribution. So we're going to create a new figure with matplotlib. Let's give it a fig size of 12 by 12 sounds good. So I'm just doing a pie chart here. Then we're going to use plot.py. And for our data, our x is going to be data subprodotto, which is, this is the product column. This is what we're trying to predict, right? So I want to know what's the distribution, like the skew of the classes. How evenly distributed are the examples into each class? So we're going to use the value counts method of this product column. And if you want to know what that looks like, so get the data subprodotto dot value counts, and you can see we get a number of examples in each value. So this is what we're going to use for our pie chart. So we're using the value counts as the actual values, and then for our labels, we're going to use the value counts dot index. So what that does, if we just do dot index, we'll just get this part, which is the names, which is what we're using as the labels on our pie chart. Dot index. Alright, then I'm just going to give it some markings. This is auto %. This is going to just allow us to display the percentages on the pie chart. And then for colors, I'm going to use a Seaborn color map, color palette actually. Rocket, just to make it look nice. Alright, and now we're going to show. And you can see each class is given a new section on the pie chart, and we can see the distribution. Looks like these four actually have even amounts, and then these two have less amounts. So with this, I want to, okay, so we're going to come back to this later. I'm going to create a series of class weights when we train our model that will allow us to take into account these differences in the loss function. Alright, so let's see. Keep that on there, and then let's start pre-processing again. So I think we can move on to encoding, right? Yeah, let's start encoding. Probably change this to cleaning. Alright. So let's see. Take a look at the data. What are we trying to encode? Alright, let's encode the label column first. And for this, I'm going to use the sklearn label encoder. When we have multiple classes and we don't have a specific order, we just want them to unique integers, label encoder is usually the best way, I find. So label encoder is going to be a label encoder object from sklearn, and then we're just going to encode the Prodotto column with the label encoder dot fit transform function. Alright, so this will assign each unique value in the product column to an integer. And then I can get, after that, okay, so our label encoder object, once it's been fit, has a classes attribute that gives us, this gives us the original classes. If we want to look at this, you can see that now the products have been changed to integers, but the original classes are stored in the classes. However, they're stored in the order that they were assigned to integers. So with that, we can enumerate it to get the updated values, and then turn it into a dictionary so we can see what that looks like. We can see that we can see what each product name has been mapped to as an integer. So it's good to keep this handy in case we need it in the future. Okay, so now let's see. Let's take a look at this. All right, this is what it looks like now. So what I notice is that we have mostly numerical data now, and we just have a few more nominal columns. The thing is, we don't know about this column. Because we can only see two values on it right now, we have this unit of currency and this unit of currency. I think that's what it is, right? It says our measurement unit. Okay. What we want to do is we want to know, are there two or are there more unique values in this column? Because if there's two, we can use a very simple encoding scheme, which is just change one of the values to 0 and the other to 1, and that will be a feature on its own. But if there's more than two, we will want to use one-hot encoding. So let's take a look. What I'm going to do is create this dictionary that's going to map a column to a list of the unique values in the column. But I'm only going to do it, so for column in data.columns, only going to do it if data.dtypes, data types, subcolumn equals object. So I'm only going to do it for non-numeric columns, because I don't really care about the unique values in all these. I just want to know the unique values in this one, and this one. And I mean, I don't really need to know here, but it's good to know like how many unique values we're dealing with. If there's too many in one column, we might just consider dropping it rather than one-hot encoding. But we can see the region column has 5 different values, which is fine. The state column has a decent number as well. And then here's the unit column. So there's 3 different ones, 3 different values. So we're going to one-hot encode it along with the others. And what I also notice is that we have some other columns in here. So it's saying that there's some other columns with an object data type. If we scroll up to the top where I looked at the info, we can see there actually are a bunch of object columns which should be numeric columns. And when you see that, it's usually an indication that there are actually some null values in this data, but they've been encoded in some other way. They're not numpy null NANs, but rather maybe they're some other symbol to denote a null value. So what we should do is check that out. Now let's try doing that first. Okay. Before we go into one-hot encoding, let's take a look. A quick way to figure this out is it might be easier to one-hot encode first. Yeah, I think it will be. Let's do the one-hot encoding first. So I'm gonna make a function called one-hot encode. It's gonna take in a data frame, a list of columns, and a list of prefixes. And we're gonna start by making a copy of the data frame so that we don't accidentally modify the original data frame in place. And then we're going to iterate through the columns and prefixes simultaneously using the zip function that will zip together the columns and prefixes element-wise into tuples. So the first element of columns will be matched with the first element of prefixes, and so on. If I'll show you why we're using prefixes if you're not sure. We're going to create a dummies data frame using pandas.getDummies, and it should be df subcolumn and prefix equals prefix. So let me just take this out and show you quickly. Dummies will this is the foundation of one-hot encoding. If we have let's use a column from our data. How about this one, region column? So we're going to give it a prefix R. Alright, you can see it has taken all the unique values that were originally in region and constructed new columns out of them, and it has one hot encoded each example for a given column. So you can see the original values here have been turned into ones in the corresponding column. And the prefix just puts it at the beginning of our new columns. So, one second. Alright. So what I'm doing here is I'm making these dummies out of a given column and a given prefix. And then I'm going to concatenate the original data frame and this new dummies data frame next to each other. Then when we're done, we're going to drop the original column from which we created the dummies. Alright, and then we'll return the data frame after all the columns are complete. There's our function. And now what we want to do is encode just the categorical variables with this. So data equals one hot encode data. The columns we're doing here is going to be region, state, and there's one more, I believe, this one, unit of measurement. Okay. Now we're going to give them some prefixes. I think R, E, and U should be fine. Alright, we run that, take a look at it. You can see we now have these one hot columns in the end, and the original categorical columns are gone. And so now you'll notice that all of our data is numeric. And the reason I did the one hot encoding first is because now we can easily check what's preventing these other columns from being numeric. So why don't we make a new section called missing values. So when you have fully numeric data, an easy way to check what's preventing columns from being numeric is just trying to cast the whole data frame into a numeric column. You can do this with data.asType numpy.float, and there we go. So somewhere in this data frame we have a hyphen, and as soon as we see that, it's very helpful to query the data frame. Actually, not query, but we'll use isIn. So we're going to check if hyphen is in the data, and we want to see how many hyphens we find in each column. And you can see there are a few here, which actually have 3,400 hyphens. And so these must represent missing values, right? So we notice that they're all the same number, which suggests that maybe these are bad examples. We could drop them, certainly, because we have so many examples, but we could also just fill in the values. Because we still have class data there, we can probably fill in the values with the means. So the easiest way to do this, I think, is first just replace any hyphens with missing values. So if we do data.replace hyphen numpy.nan, that's the new data, and then data equals data.fillNA. Actually, we can't fill it all at once, we have to iterate through. For column in data.columns, the reason for that is we want the respective mean of each column to fill. So data subcolumn.fillNA. And we're filling with the mean of that particular column. Set that equal. And so it's going to change all the hyphens to null values and then fill in the null values with the means of that column. However, I also realize these columns are not going to be numeric, right? Because they had a hyphen in them, they were not able to be cast to floats. So what we're going to do is, okay, so once they get null values, then they can be turned into floats. So what we'll do is .asType numpy.float.mean. So we're going to turn it into a float, get the mean, and then fill in the null values with the mean. So with that, we should check now. We're checking for null values again, and we have 0. So we're good to go. Now if we try to cast the data as a float, it works just fine. Alright, fantastic. So let's actually do that. Actually, let's not do that yet. Let's not do that yet, because I don't want our classes to be floats. I just like to keep them as integers. So we will wait to do that. We'll do that once we split the data. Alright, so splitting and scaling. Now our data is fully numeric. Okay, there are no more text values in our data. So what we're going to do is split into two sections. Y will be what we're trying to predict, which will just be the product column, and X is going to be everything except the product column. Alright, then we'll scale using the standard scaler from sklearn, which will give every column in X mean 0 and variance 1. X equals scalar dot fit transform X. I realized I didn't actually create the scalar object. Scalar is going to be a standard scalar, which we imported from sklearn. Alright, so we scaled X. It's interesting. I didn't actually ever turn X into floats. It was still, let me see this, data.dtypes. See, there's still some objects here. Even though it's fully numeric, supposedly, there's still object types. But it looks like the scalar fit transform function automatically converts to floats, which is nice, because that means we don't have to do it ourselves. X is going to be all floats stored in a NumPy array now, so we should be good to go. Alright, so I'm going to split that further into xtrain, xtest, ytrain, ytest, using the train test split function from sklearn, and we're passing in x and y. I'm going to specify a train size of 70%, and we'll give it a random state of any number. 34 is good, just to be able to reproduce our results. So I'll split that, and now we will start training. So I'll create the model. It's just going to be a standard neural network with two hidden layers. Inputs, it's going to be our input layer, tf.keras.input. The shape here, we should get that. Let's go to x.shape. And this is actually a good time to calculate our class weights. So at the top, I imported sklearn.utils.classWeight. Class weight will allow us to compute the class weights pretty easily. So we can do this by saying class weights. Wait, class weight is the name of what I imported, and it has a function compute class weight. And so this function will take in a mode of weighting, which we're going to do balanced weighting, and then it's going to take a set of classes, which will be the unique values in ytrain, and we are only doing it on the train set here because that's all we're going to be using class weights for. And then it's also going to take in the data itself to find the class weights from. So that will just be ytrain. Alright, so that gives us a bunch of class weights here, as you can see. But let's turn it into a dictionary that TensorFlow can recognize. So what I'll do is I'll enumerate it. And then I will turn that into a dictionary. Okay. And then let's call that class weights. Alright, here's our class weights. Just take a look at the bottom. Here it is. Each class has been assigned a given weight based on the distribution of the classes. And you can see these two we can see that two of them, it's interesting. I might want to, no, what I could do is change the using the original dictionary that we had that mapped, where is it? This dictionary. We could also just switch out a integer for the original name of the class down here, but for our purposes this will be fine. And you can see that two of the classes have higher weights, and that's to account for these two classes that have lower percentages. So the smaller the amount of classes, the higher weights they'll be given to consider in the loss function. Alright, so for the shape, this will be the number of inputs that we have, which will be 49 features. And then we're going to create two hidden layers. One will take in, here let's give it 64 activations and a ReLU activation function, and we'll pass in inputs. And then we're going to do the same thing for the second one, but we'll pass in X. And for outputs, we're going to do another dense layer. This will be our probability estimates for each class. And so we should probably see how many classes we have. So y.unique. And we can see we have 6. We get the length of it. We can store that in num classes. And then pass num classes into here. So we have 6 classes, so it's saying 6 activations. And we're going to give this an activation function of softmax, which will give probability estimates for each class. Alright, passing in X to that one, and then we'll create our model, which will be tf.keras.model, passing in inputs and outputs. And now we'll compile the model. So we'll give it an optimizer of atom, a loss function of sparse categorical cross entropy for multi-class classification, and then metric we'll use will be accuracy. Alright, give it a batch size of 32, and I'm going to use early stopping, so we're going to, doesn't really matter as long as we have sufficiently large number of epochs. And then we're going to store our model's fit history in history and train the model on the train set, xtrain, ytrain. We'll give it a validation split of 20% and pass in the batch size and number of epochs. Alright, then I'm also going to specify a callback function, which will just be tf.keras.callbacks.earlystopping. And this is just going to do an automated early stopping whenever our model's loss starts, the validation loss starts to increase again. So this is to prevent overfitting over time. And we can specify which value we want to monitor, which will be the validation loss. And we also want to give it a patience, which is how many epochs are we willing to wait before we'll consider consider stopping. So I'll say 3. 3 is pretty good. If the loss continues to go up after 3 epochs, we will stop right there. And then we're going to call restore best weights. We'll set it equal to true, which is just going to, once it stops, it's going to set the model to have the weights from the best epoch. And we'll turn this verbose mode on so that we can see what it says when it stops. Alright, and then one last thing, I'm going to pass in the class weights that we calculated. So class weight equals class weights. And let's train. Alright. And while that goes up, I guess we can just write results here. And we'll evaluate this on the test set. Now I used to always create a plot here of the training and validation loss over time, but because of this early stopping callback, there's really not much need to do that, because We don't need to track when the validation loss starts to go back up again because this does it for us already, although there may still be some benefit. And you can see it has early stopped at epoch 13 and has restored the model weights from the end of the best epoch. So if we now evaluate this on the test set, we get a final accuracy of 91%, which is fairly decent. I think there's probably we could do things to improve this model, but I think that will sum up today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.